Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHGTool Cloud. And today we'll be doing another exercise together, namely on the design of collective borefields. So the case study for today is an apartment building with 80 apartments, which are all connected to a collective borefield. Now, in a previous exercise, we focused on, how do we design a borefield for a single building? And now we will be looking at a collective approach. So today we will be learning the difference between the individual and this collective design approach. We will learn the importance of the peak duration when it comes to borefield design. And we will talk about simultaneity and how it relates to collective systems. Now, let's first go over all the different input information. So in general, we will design with a minimum average fluid temperature of 0 degrees and a maximum temperature of 17 due to passive cooling. We are working with 25 years as a simulation period, and the first month of the simulation will be January. We have a ground thermal conductivity of, assume a constant 2 watts per meter Kelvin, volumetric heat capacity of around 2.4 megajoules per cubic meter Kelvin. We have a surface temperature of 9.6 and a geothermal flux, which causes a gradient, as you know, of 0.07 watts per square meter. Now for borehole resistance, we will use a WDN32 for this case, a borehole diameter of 140 and spacing of 35 millimeters, with a standard grout, let's say, of 1.5 meters watts per meter Kelvin. And we will use 25 volume percent of monopropylene glycol with a flow rate of 0.21 kilograms per second for each apartment. So we will assume that each apartment has its own heat pump, with its own circulation pump, which can deliver 0.21 kilograms per second. Now for our loads, we have a heating demand of 3.4 kilowatts for each apartment, giving us a yearly energy demand of 5.1 megawatt hours per year. For cooling, it's 2 kilowatts with 1.4 megawatt hours per year, with a certain efficiency, and our domestic hot water is 1,600 kilowatt hours per year per apartment, which is around 2 persons that live in each apartment. Now, before we start, I want to recall also the simultaneity. So when you're working with collective systems, and in this case we have 80 different apartments all connected to the same borefield, well, we can assume that the peak power, the total installed peak power of this entire system, it does not occur all at once. And Winter et al. Has done some research, and they have found this correlation where, depending on the number of uses, you can decrease your peak power. Now, for 80 apartments, we're around here, so we see that around 63.26% of our total installed power, 80 apartments multiplied by 3.4 kilowatts in heating, only 63% of that will be simultaneous. And next to this simultaneity, we also had the concept of peak duration, where we say, okay, it's not only the peak power that changes. Okay, we have a lower resulting peak power due to the simultaneity, but the duration of this peak increases. And there was no real research about that. So in a previous video, linked in the description, we said, well, we can do a first estimate based on the central limit theorem, where we can say that the peak duration of our collective system, that it scales proportionally to the square root of the number of uses, which is kind of a heuristic. And it gives us this curve where we know that when we have 80 apartments, around a factor 9 increase in the peak duration should be expected. So now that we know again what simultaneity is, let's jump right into GHGTool Cloud and discover how we can design this collective borefield together. So here we are in GHGTool Cloud. I created a new project. So before we start, let us fill in all the required information we discussed before. So let's use 0 degrees and 25 years as a simulation period. For ground parameters, we had ground surface temperature of 9.6 with a geothermal heat flux of 0.07. Now, it can be that this information is not available for your project, then you can just use a database. But in these exercises, I really want to show you how flexible GHG tool is. So that's why now we're going to enter this manually. For this first scenario, we will just design a single apartment. So let's keep it to one borehole. And also as the aim, I will calculate the required depth, which will be useful, I think. So we have a W tube, 1.5 or 40 with 25% of monopropylene glycol and 0.21 kilograms per second as a flow rate for our single apartments. And our thermal demand, it had 1,600 kilowatt hours per year as a domestic hot water demand, 3.4 kilowatts in heating, 2 in cooling, 5.1 megawatt hours, and for cooling it was 1.4. So now let us go ahead and simulate this scenario. So now we will simulate the situation for a single apartment. What's the required borehole depth for a single apartment? And we find out that one apartment needs one borehole of 96 meters deep. And as you can see here, we're limited by our cooling peak. So we do not reach our minimum temperature of 0 degrees. We stick at 1.45 degrees Celsius. Now, let me go ahead and rename this to scenario 1, single apartment. So, now, based on this information, let's go ahead, duplicate the scenario and do it for the whole apartment block. So we had 96 meters. Let us go ahead, calculate the temperature profile for boreholes of 96 meters. We have 80 apartments, so let's use 20 by 4, something like that. So we have 80 boreholes, 96 meters. Our borehole resistance, the flow rate changes, so now we have 80 apartments, which will give us a flow rate of 17 kilograms per second. I calculated this before. And for our thermal demand, this of course also changes. So let me open up my calculator. So we have 1,600 times 80, which is 128,000. For peak power, I know that by heart, it's 272. 5.1 times 80, it's 408. For cooling, it's 112. And maximum cooling, that's not that hard, that's 160. So let us now go ahead and simulate this for the whole apartment building. And what you would expect is that it fits, but it does not, as you can clearly see here. So as you can see, where our single apartment, it's fitted nicely. Here, this is not the case. And that's because we have now 80 apartments. So all the 80 boreholes, they work together, and the imbalance, which is just 80 times the imbalance from before, which was not clearly visible here. And we started with 2.4 and we ended with 1.45, is way more significant when all these boreholes interact with each other. So here we already learned an important lesson. We cannot simply take the borehole length from a single apartment and multiply it with 80. We will end up with a totally wrong design. So let us go ahead and try to fix this. Call it fix, super original. And let us, for example, say use 150 meters deep. So just to see how it turns out, and surprisingly it works rather well. So if we go from our original 96 meters to 150 meters, we now beautifully fit into this temperature threshold we set. And as you can see, we're also not longer limited by the minimum temperature, but really in the long term by this, due to this imbalance. But of course, we go from 96 meters per apartment to 150 meters, which is quite a lot increase in our design. Now things become interesting, because now what we did is we said, well, okay, our thermal demand, we took one apartment, we multiplied it by 80. So we basically assumed 100% simultaneity. Okay, because we said, well, the total peak demand on a building, on a borefield, is exactly the same as all of our apartments working together. So let us now go ahead and make a fourth scenario with and let's just call it simultaneity. So with simultaneity, our yearly heating and cooling demand stays the same, but as we said before, we had 36.26%. So make it percent and multiply that by 272, which will give us 172, and do the same with 160, which will give us 101. Let's go ahead and simulate this now. So now we did is we said, okay, we had 63% simultaneity, we lowered our peak powers, and now you can see that with the 150 meters, we are way above our temperature threshold. So now we have oversized our borefield. Well, of course, instead of 272 kilowatts of heating, we only have 172. So of course we do not reach the limit here. But as you see, we kept the peak duration the same. So saying, okay, a single apartment, when the heat pumps work at the maximum power, it works for 8 hours straight at that maximum power, which is an assumption we need to make when we are working with this type of monthly load profiles. But of course, when we go to a simultaneity factor, this peak power duration, it increases. So this is not really an accurate simulation, because if we have 80 apartments, we lower the peak power by 63%, but it will have, of course, a higher peak duration. So for a fifth scenario, we will say we will have a higher peak duration. Now, when we have this peak duration, we know we had it scales proportionally to the square root of the number of apartments, which is 80. So it's almost 9. So for our peak duration, we can say 72 hours. And let us go ahead and simulate this now and see what results we will get. And here we see that we are at 1.39 degrees. So there is, what is it? 0.35 degrees C difference between both. So it's still better than just putting the whole power onto the borefield. Of course it is, because there is simultaneity. But this result is already a lot more accurate, I would say. Now, as a final design, I want to use the newest methods for collective systems in GHGL, because now we worked with this heuristic to translate or to upscale our peak duration from an individual to a collective system, using the square root of the number of systems. But this would mean that it's the same for all locations on Earth, whether you're in the coastal region or you're in the center of a country. It all scales the same way, which is a little bit weird. So let us go ahead and go for the whole apartment block fix, and let's duplicate this scenario and call it scenario 6. Upscale to hourly load. So, as you might have seen, we have here this button to create an hourly load profile. And what it will do, it will take our maximum power in heating and cooling and it will convert it to an hourly load. So let us go ahead and select a location, and let's say that this project is located in the city of Bremen, Germany. Let's say it's located there. Doesn't really matter, just to show you. So it will find the weather file for that location, and we say we have a collective system of 80 buildings, which means that we have indeed a simultaneity of 63%. Let us go ahead, create an hourly load profile, and this is the profile we have. So if you recall our video on this specific functionality, what we do is we take the weather profile and we try to fit our peak demand and energy demand onto it, and then we're going to limit our peak power to exactly the heating demand that or the peak demand that we have installed. So let us go ahead and use this hourly profile, and let's simulate the result now. So when we use this method, since we're limiting the peak power, it also automatically increases the peak duration because we're now working with hourly loads. And as you can see, we are here at 0.82 degrees, whereas before we were at 1.39. So there is quite a big difference between those two methods, and as you can see, this is the reason why. So normally you would expect your load duration curve to go steeper, but we limit it to 172 your simultaneity, and this you can see here clearly in our hourly graph as well. As you can see, we start around January 21 with 172, and it is almost a week or more than a week, 10 days, that we're at this maximum power. So our peak duration, when we use this method for this specific location, is way bigger than our 72 hours. So I would be tempted to say that this methodology is actually a little bit more accurate, because here we had a peak duration of 72 hours, but if we look at a typical profile generated based on the weather data, you would expect way longer peak duration, which you can also see if we, for example, zoom in on this last year. You see here that it's really going steep down, and this curve, you recognize the G functions. If you're not familiar, check the description, but it lowers continuously in temperature due to that long peak duration and simultaneity. So I would say that this is the more accurate design. Now for our final scenario, let us just recalculate the required borehole depth. Update with this hourly profile to see how our design, our required borehole length, is different from when we design a whole apartment block, which was with the fixed length 1190 or 11,920 meters, and when we use our hourly profile, we have a required borehole length of 11,100. So we save 800 meters, when we use this more advanced method for calculating simultaneity in collective systems. So I hope you found this video interesting and you learned a lot about simultaneity and peak duration and how this upscaling method can actually help you in your particular projects to design a collective borefield system. If you did, please consider subscribing, sharing this with your colleagues. If you do this exercise, please try it yourself before watching this video. You will learn more if you do it the other way around. And I'm looking forward to seeing you in the next video. Take care. Bye.